All right, let's get right into it. For decades now, we've had this really successful story about how our universe works. But it's a story with a huge main character that we know almost nothing about: dark energy. I mean, this mysterious force makes up something like 70% of everything, and it's the thing that's pushing our whole cosmos apart, faster and faster. But here's where the story takes a massive plot twist. The standard thinking has always been that this force is constant, unchanging. But what if that's wrong? What if the push from dark energy has actually been evolving over the entire history of the universe? Well, some incredible new evidence is suggesting exactly that. And honestly, it could change everything we think we know.
So, to really appreciate why this new evidence is so groundbreaking, we first have to get a solid handle on the current accepted model of the cosmos. Think of it as our baseline, the theory to beat.
That model has a bit of a mouthful for a name. It's called ΛCDM, and it has been wildly successful. It describes a universe that's governed by Einstein's general relativity and is, on the biggest scales, pretty much the same everywhere. That little lambda symbol in the name, that stands for dark energy.
And this chart just brilliantly shows how much of a big deal that lambda is. According to this standard model, everything we can actually see and touch, all the stars, planets, you and me, that's just a tiny little slice of the universe. The rest is this cosmic mystery, split between dark matter holding things together and the huge majority, dark energy, pushing it all apart. So here's the absolute key point. In this standard story, that lambda is a cosmological constant. It's supposed to be a simple, unchanging energy that exists in empty space. Physicists have a way of describing its strength with a number they call W, and for a constant, W is always exactly -1. Not -1.1, not -0.9, just -1, forever. That has been the bedrock prediction. Okay, so if you're going to challenge a prediction that fundamental, you're going to need some serious detective work. And luckily, that work is being done by a really remarkable new instrument. Meet the Dark Energy Spectroscopic Instrument, or DESI for short. And to really get a feel for its power, just look at this number: 5,000. DESI is kitted out with 5,000 tiny robotic fiber optic eyes that can all measure the light from 5,000 different galaxies at the exact same time. It's an absolutely unprecedented cosmic map-making machine. And DESI's whole mission is to use those thousands of eyes to build the biggest, most detailed 3D map of the cosmos ever even attempted. By measuring the positions and distances of tens of millions of galaxies and quasars with insane precision, it can literally trace the entire history of how the universe has expanded. Now, to make these measurements, DESI uses this really fascinating tool. It's looking for something called baryon acoustic oscillations, or BAO. It sounds complicated, I know, but you can just think of them as fossilized sound waves from when the universe was just a baby. Back when the cosmos was this hot, dense soup, sound waves rippled through it, and they left behind a pattern, a standard length, that got stamped onto the very fabric of space itself. So how does this cosmic ruler help us build a map? Well, that initial sound wave set a fixed standard length. Billions of years later, galaxies were just a bit more likely to form along that ancient imprinted pattern. So, by finding that pattern today, DESI can measure how much it seems to have stretched out because of the universe's expansion. And measuring that stretch at different times in cosmic history is how we can map out the expansion with incredible detail. And it's from this incredibly precise map that DESI has uncovered some genuinely surprising clues. Clues that are really starting to challenge that standard story we've been telling ourselves for years. The obvious question then is, what did this revolutionary new map actually find? What is it telling us about this dark energy? And here it is. This is the headline result. On the left, you've got the prediction from our standard model, a constant dark energy where W always equals -1. But on the right, that's what DSI's data is pointing to: a dynamic, evolving dark energy. Specifically, it implies that way back in the past, dark energy was actually stronger than the standard model allows for, with a W of less than -1. And today, it's become weaker, with W being greater than -1. Now, this evolution, this isn't just some small tweak to the theory. It implies that dark energy has done something that, according to our simplest models, should be totally impossible. It looks like it has crossed a forbidden boundary.
That boundary is called the phantom line. It's that exact value of W equals -1. The whole reason this line is so important is that our simplest, most elegant theories about dark energy all predict that nothing should be able to cross it. For W to dip below -1, even for a little while, it would have to violate some really fundamental ideas about how energy and gravity are supposed to work. It would mean the force driving dark energy is way more complex and exotic than we ever imagined.
And look, this isn't just some vague hint or a statistical blip. The DSI results show a deviation from the standard model that's statistically significant. We're talking somewhere between 2.8 and 4.2 sigma. To put that in simple terms, this is not something you can just brush off as random noise. The data is clearly pointing towards something new.
And the researchers themselves are being really direct about what their data implies. This quote from the collaboration just sums it up perfectly. They aren't just saying it's a possibility, they're seeing a clear preference in the data for models where dark energy actually crosses that phantom line.
So the evidence is strong and the implications are, well, profound. This whole thing forces us to ask some very deep questions about the very nature of our universe and the forces that run it.
The central question isn't really if dark energy exists anymore, but what it is. If it's not the simple cosmological constant we've been assuming it was for all these years, then what kind of new physics could possibly be going on?
And scientists are already on the case, testing out new suspects to explain this strange behavior. As you can see here, some of the leading alternative ideas are already running into trouble. So-called thawing models, where dark energy evolves but can never cross that phantom line, they're a poor fit. Emergent models, where dark energy just kind of pops up late in the universe's history, also not favored. But a newer class of mirage models, which suggest much more complex goings-on in the dark sector, they seem to be an excellent fit, almost perfectly matching what DCIS has observed. And what's so crucial here is that this isn't a fragile result. The DESI team stress-tested their findings like crazy, using a bunch of different approaches. But no matter how they sliced the data, the main result stayed the same. The evidence for a dynamic, evolving dark energy is robust.
So we're left with this absolutely tantalizing question. For 50 years, the standard model of particle physics has stood strong. For the last 25, the standard ΛCDM model of cosmology has done the same. But now, with this new precise map of the cosmos, are we finally seeing the first real cracks appear in that beautiful, simple, and maybe, just maybe, incomplete picture of our universe?